Okay, so good morning, and today we continue uh, the specific heat of solids. We will be studying the second model, which does a better job of matching what we see in experiments. Okay, so this is a recall. So the model which we discussed was due to Einstein. Okay, I will talk a little bit more about the Einstein model in a moment, but in the Einstein model, what uh, so there are three n normal modes. Three n modes have the same frequency, which we call omega. Okay, and the specific heat in that example where xi is just okay. So high temperature is xi going to zero. So we can just do that. So this is for T. So we need some scales. So we'll just say kBT is much greater than h bar omega. Then xi goes to zero. So if you just look at that thing, this goes to 3n kb. And the other limit, which is kBt, being much less than h cross omega, which is xi being very large. And so this will go like 3n kb into xi, and sine hyperbolic of xi will go to e power xi. So there might be a factor of 2 probably, divided by 2, probably into 2. But anyway, that's not important. Okay, so this is what you get. I just was taking limits here. And so what happens is that, so this is an agreement with experiment, and that experiment is we could do long and Petty kind of thing. So it's called the DeLong-Petty. It's an experimental law. It just says this thing. And the behavior is C. This tends to zero, of course, as xi goes to infinity. Even though xi square is going to infinity, e exponential falls off faster than any polynomial function. So exponential wins. So it goes to zero. But this is wrong behavior. Okay, but it is exponentially fast. So what is observed is it goes like, it should go like t cubed to 0. So for small t, so of course t goes to 0. So this is what we expect for the ionic contribution. It doesn't do that. Okay. So the Debye model addresses this issue. Okay. So let's look at that. Okay. So before we do that, one obvious problem with the Einstein model is that it assumed that all normal modes have the same frequency. Which we called omega. Okay. But from our classical mechanics, we know the following thing is that okay, if you remember, we did small oscillations. Okay, so there will be a bunch of normal modes. Okay, so there will be a spectrum of normal modes. Omega 1, omega 2, will be omega 3, and some of them might be equal, etc. And we also know that one of them will be 0 also. The overall translation will be. Okay, so this is what we know. Okay, so this is the, so okay, so we can correct. Okay, so we should so we should. Okay, but I mean, but the issue is that it is not easy to compute the normal frequencies. Okay, so 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 what we will do is, and that is one thing. Further, we want to take the continuum limit. Okay, so this is what we want to do. So it's really not something which we need to do, but so the idea is that what we do is we'll define as. Okay, so what we do is we define a density of states, which I'll call rho of omega, in the usual fashion. So that means, what I mean, rho of omega d omega or delta omega equal to total number of states of angular frequencies, angular or normal modes. Let's see, in the range omega to omega plus delta. So this is the usual definition which we had done earlier in this course also. Okay, so let us write some formulae for rho of omega. So rho of omega in the Einstein model will be very simple. It will be 3n into delta of omega minus omega naught. Okay, so I called some frequency omega, same frequency omega. I want to call it omega naught because I want to use a variable, this thing. So I'm just putting that. So that's the Einstein model, right? There are 3n of them, and they all take the same frequency. And but if you have the normal modes properly, then we can do something better. I equal to 1 to 3n. Okay, so this is exact. Okay, is this clear? Hello?
Yes, sir.
Yes.
Okay, okay. So this is clearly what we want, but what we want is a continuum. Okay, but what we want to the second expression really. Okay, so but we can't do it exactly. So we will do a semi-classical computation. Okay, so what we will do is okay, and this is based on associating a particle, okay, to the vibration, to the normal mode. Okay, so this is analogous to photon to the electron, to the electromagnetic field. If you go to quantum mechanics, this is what you will get, and this particle is called a phonon. Okay, so what we would say is that so for instance, so we'll say that here's what we would say: a phonon. So remember, omega i's were the normal modes. So we'll say a phonon of energy h cross omega I. Okay, and then it can have momentum also, and it can have momentum which will be some h cross some vector I. Okay, this is what we will say. But then we have to also specify the dispersion relation, and this is a key important point, is that how is okay, and the answer is not h cross square k square upon 2m. The reason is that these excitations are, in a sense, these phonons have zero, are massless excitations. Okay, so they will have, it will look something like a relativistic thing. So what you will get is omega. So I remove the subscript I. It could be any one of those things. So what you will see is omega will be equal to Cs times k, where k is the magnitude of. Okay, so the subscript here. Okay, so this here is not the speed of light. So this, if you remember, the for photons, omega is c times k, right? Where c is the speed of light. So what should replace the speed of light in vibrational things? Things won't move at
Sound.
sound. Yeah. Okay. So speed of sound. Okay, so this is very very crude. I mean, crude in the sense that there could be, uh, anisotropies. So you could have, there are transverse modes, longitudinal modes, and they need not have the same speed. But we will be very cavalier. We'll associate one speed. Okay, because we need to do something very very simple. So this is called the dispersion relation or the energy momentum relation. Okay, so this is what we get. So this is what okay, so if we have n phonons with frequency omega, okay, then the energy would be, total energy, what will it be? N h times h cross omega. Okay, so this is the multi-particle picture, and so this is what happens. Okay, so what we want to do is, so now we are ready to do this thing. So what should I, so so what we are doing now is we have a particle interpretation of the story. We have a dispersion relation, so we can just go ahead and do what we would have done with a regular particle, right? So if you remember, we would do rho of omega delta omega should be equal to, now I will write something, dqp for a single phonon. So this is we are looking for phonons in the range omega plus delta day. Okay, so this is with energy or frequency belonging to h bar times omega and omega plus delta omega. Okay, is this clear? So this is a semi-classical one. This is what we did for a free particle, something like in a particle in a box and things like that, right? Same thing. Okay, so easy thing, we can do the x integration that will give you the volume of the solid. Okay, and since P equal to h bar k, I can convert this integration, okay, as follows by 2 pi. This is h, so I need to divide and multiply by 2 pi cubed. Is this okay? Again, energy condition is still there. Okay, so now I can go ahead, since the energy only depends on the magnitude of k, I can just go ahead and integrate out. I can do the angle integration. So in k space, I can do the angle integration. So I will just get v into 2 pi whole cubed into 4 pi into k square dk. And this condition, energy belongs to okay. So now we can just use the dispersion relation, which is omega equal to csk. So it just says that dk will become d omega by cs, okay, and k square, etc. So this will just tell us that rho semi-classical of omega is v into 2 pi whole cubed into 4 pi into omega square, and there are 3 powers of c, so divided by cs. Okay, I'll pause here. Does this make sense? So we have an estimate for rho. Okay, let me just do some cancellations. So 4 and there'll be an 8 from here, so that will become half. So we'll get v by 2 at pi square cs cubed omega square. Is this okay? Any questions, comments with regard to this computation? Okay, but this has a problem. Okay, if you have free particles, all values of momenta are allowed, or all values of frequency. Okay, we know that normal modes have an upper bound. Okay, because there are only finite number of them, right? Of course, it goes to infinity. So Debye said that introduced a cutoff. Okay, and so I'll write that rho of omega will be equal to whatever we wrote here. Some omega d, okay, and it is 0 for omega greater than omega. Okay. So if you plot it, it will increase quadratically till omega d and then becomes 0. Okay, this is clear. This is what it looks like. So this is the final. So we have this is semi-classical, of course, but we have a nice model which includes the cutoff which Debye put in, which is a reasonable approximation. Okay, so now, but we still need to what determines omega d.
The integration should be 3n.
Exactly. Okay. So what this implies, okay, is that so we can substitute this. No need. I'll write one more line. So what was it? V by 2 pi square 6 pi square Cs cubed. Okay, so this determines, okay. So this is what happens. This is what you get. Okay, so it grows like n power one third, but it is still some finite. I mean, it's just some number. Of course, there's also a factor of volume, etc. So, okay. So, so this is what. So what Debye has done. So there is only one. So we can. What you can see is that in the continuum limit, we can forget about. So omega d is a free parameter from our viewpoint. Okay, and so we can trade speed of sound, v, etc. for just this single free parameter in the model. We are not done with the Debye model, but still, it's a free parameter in the Debye model. Okay, so it's useful for us to ask, can we rewrite? So we can go back and rewrite rho of omega in terms of omega d. Okay, if you just do that, you get something like this: 9n omega square by omega d cubed. Okay, it's just the same formula which we wrote here. Okay, but what I've done is I've traded all these occurrences of VECS cubed into omega d cubed, 1 by omega d cubed. There are some constant factors, etc. This is what you get. But what is crucial is that it's proportional to n, which you like, which one should like. Okay, so we are almost done. Okay, so now we need to compute the total internal energy. Okay, so I mean, this is for omega less than omega d. Okay, okay, so rho of omega we have computed. What is this n of omega? So, so the whole point is rho of omega tells you what is the number. It gives you the number of phonons in that with that frequency omega and with some width. Okay, that's what it tells you. But we can have multiple phonons of the same omega. So we need to know. So n of omega is the average number of phonons with frequency omega. Okay, so we need to do a computation, and I'll do that now. Once we do that thing, so and I forgot something else. Because the energy of that phonon will be this. Okay, so n h cross omega, but there will be how many of them that we know. Okay, so that's the thing. So we need to estimate n of omega. What is n of omega? It is just the expectation value of the number of phonons with a particular frequency. Okay, so that will be summation. We are in the canonical ensemble. N times e power minus beta. So this is omega is fixed. So if there are n phonons of frequency omega, what is the energy of that? N h bar omega. But you have to normalize it. So that will be to get the probability. Okay. So you can, these are all geometric series. This is denominator is geometric series. And the other one is d by d, derivative of a geometric series. You can do this calculation. But I'll write this formula, and this is an important formula. It's beta h cross omega minus b. Okay. So this is a very famous formula. We'll come back to this later in a more sophisticated thing where we'll add something called chemical potential. We'll let the number of photons fluctuate, which is what I'm doing here. But there's a much more elegant way of doing this. But I'm at this point not worrying about elegance. Hello, can you hear me?
Yes, sir.
Okay, thank you.
Yes, sir.
Yeah, no, there was a power outage here briefly, so sometimes. Okay, so we are done now, right? So what we have is we have computed this, this is nothing to compute, so we are done. So we just have to do an integral. Okay. So now not explicitly, but you can just go ahead. We'll plug everything in and we'll get something like this. There's some change of integral variables which you need to do. And that's very easy to see what that is. So you come here, this is, we're just calling this quantity x. So xd is just h cross omega by kbt. Okay. So in problem set 7, I defined this function for you, and we call this function d of x. This is the definition. Okay, it's called the Debye function. Okay, so this is indefinite. I mean, we have to do an integral only up to xd. Okay, this is where xd dependence comes in. And of course, why have we put these factors? I mean, the reason is that for large t, so there are some properties that we will work out of d of xd. In particular, this 3 by xd cubed is put there so that we get 1 at large temperature, high temperatures, which is for small xd. Okay, and that's very easy to see. For you have to do it as a limiting process. So you will see that when it goes to 0, e power xd minus 1, so there'll be some cancellations, and then it'll be approximately x square. X goes to 0, numerator goes to 0, denominator also goes to 0. L'Hopital's rule will tell you that it'll become some x square or something like that. So you'll get these factors and they will just cancel, and you will get this. It'll go as 1. It's not very hard to check this. Okay, so okay, good. So that is why we want to pull out this thing. But for low temperature, we have to do some work. So problem set 7. We were asked to show. Okay, so this is 1 minus. I felt y less than 1, and it goes like y cubed plus, okay. So, and remember, it depends on its inverse temperature. So what is y less than 1 is low temperature or high temperature? Y less than 1.
High.
Okay. So this 1 is just now what I mentioned, and this is the low temperature. Okay. So now we are ready to look at U at low temperatures. But what I want to point out here is that this is exponentially suppressed. It's not. Okay. So really we can, so if you just go ahead at low temperatures, we can just go here and replace. So at low temperature, okay, low temperatures really is that H cross omega is much greater than kBt, or kBt is much, because there's only one dimension. Okay, so omega d. Okay. So this is what we have. At low temperatures, U will be 3n kBt divided by y cube. Okay, so into pi power, what was it? 5y cubed, but what is y is okay, so what we can see here is U is proportional to t power 4. Is this clear? And C, so now we can C is, at least at low temperatures, this was the problem. Okay, C is now, what will C be? It's just du by dt, right? The desired dependence. Okay, so, but actually you can go ahead and do some work and you can get explicit formula for arbitrary t. You can differentiate. To get C. So let me write what you would get from that. Again, 3 nkb is the answer at high temperature. Okay, but by integrating by parts, there's a nice, cute result that you get. Well, d of xd is the same Debye function that we. So we have both are equivalent. You can do both things. So this is what we get. Okay, so we are more or less done. And in problem set 7, I asked you to do some plotting, and so I want to look at that plot. But I'll pause here before I do that, show you the plots for questions.
Yes, sir.
Yeah.
About the problem set 7, you asked to prove that question. So how we should be doing it by Taylor series expansion?
Yeah, so yeah, good question, good question. So come back to let's look here. So where was the definition of Debye function? So let's do for y
Here,
less than 1. Okay. So where was the definition? Here. Where is the definition? Oh,
B,
somewhere here. Here it is. Okay. So if xd is much less than 1, x is also less than 1. So for that you can just go ahead and write e power x as 1 plus x square. You do those things, truncate at whatever order. Minus 1 will come, there'll be an x cancelled, and then you expand it. Just do that. So that will give you this expression. But the other expression is when xd is very, very large. So then what you do this, you write this integral as 0 to infinity minus integral of xd to infinity. Okay, so then the values of x, so you write integral 0 to xd equal to 0 to infinity. Now this definite integral, you can write the answer, it is some pi by 5 or pi power 4 by 5 or something, some zeta function it is, minus integral. Okay, so this gives you the first term which I wrote. This term, let's look at that. So x is very, very, the smallest value of x there is xd. Okay, the smallest value of that is also very large, so you can just e power xd is much, much greater than 1, so you can drop this 1 and write it as e power minus x, or you can okay, so then you can go ahead and do the integrations. So you can write the answer. You can do those integrals, but you will see immediately that the leading term is order e power minus x. That's all. So that's the O. Okay, that's how I did it. I don't know. Okay, good. Is that clear? Did I answer the question?
yes, sir.
Okay. So, okay, so now, if there are no more questions, let me go to the figures. Okay, so the first one, you can see the figure, right? So the first figure is u over n versus t. Okay, so here I haven't labeled it, but I will do it now. Okay, so let's do that. Great. So the black line is Einstein model, and blue is Debye. Okay, so for blue I just plotted the Debye, but the Einstein model I had to do something. Einstein model doesn't go to 0, okay, because this is the 0-point energy. So when I did the computation of the Debye model, I did not worry about the 0-point energy. So because there will be some additive constant to u, we were interested more in looking at the specific heat, which is one derivative. So that constant is not important. But here I want to make these two guys this thing. So what I found was that when I plotted the two functions, and there was some work to be done, what you find is that you need to shift. I shifted down the Einstein plot. That means subtracted some constant, and I did it such that the behavior, so that they agreed at large. So they agree here. Okay, so but you can see that this is the so they won't. So obviously, I could have done the opposite, which is to move. Anyway, I'm not putting any scales here. So equivalently, I could have moved the Einstein plot, Debye plot upwards, okay, and that will give you the 0-point energy, okay. So, but I mean, this difference has no meaning, but it just reminds you that there is the way we have plotted the Debye thing, the u goes to 0 at t equal to 0, okay. But it won't be true. There will be some constant, okay. So that is just this thing. So here, what I've done is to get them to match, okay. There won't be no such issues when it comes to the specific heat, okay. So let's look at this thing. Okay, so let's make this bigger. Okay, so now let's look at this. Black is the Einstein thing, and you can see it falls to zero very, very fast. So this is the exponential fall off. Okay, and the blue curve, and you can see that there are, can you see the dots? Can you see the dots in the lines? So I'm doing it numerically. So I do numerical integration. For each value, I just did some bunch of things and I adjusted this thing. So actually these are a bunch of dots. I have not connected them or anything. So what you see is that this goes slightly differently, but asymptotically you can see they all agree at high. They all go to 3n kb. Okay, but one thing to observe here is that the Debye thing goes faster to 3 kb than the Einstein one. Okay, eventually at infinity they will all go to 3 kb, and the dotted line is just giving you the asymptotic. Okay, this red line is just I take the truncation of the low temperature behavior. I only take the first term, that is T cubed. Okay, and so that should agree with this for low temperatures, which it does. Okay, so this is the plot you should get. So this is what is a T cubed. So a T cubed with some prefactor, etc. So those prefactors are, I mean, I don't do anything. I just take the thing, truncate, plot it. Okay. So there is some work that you need to do to make sure that you get all these things correct. This was easy for me, but this one was a little trickier to, to get all the scales right. But here there is nothing. No, I didn't have any free parameters or anything to play with, and so this is what we get. Okay. So so you can see, I mean, here's what I'm saying, here's the thing, I plot these two guys. I was telling you, you just plot it, I'm going to use, some program, no problem, I can do it, but that's not it. The point here is we have to ask what is it we want to match. So what I've done here is the physics of the problem, which says that for large thing, these two agree. So let's make them agree there, and then look at what happens at low temperatures. So what we see is that they do not agree at this thing, but it also reminds us that we did not take the 0 point energy of the phonons. There could be some 0 point energy, and there is actually. Okay, so that's what we get. But here we see a nice, completely really neat behavior. Here I didn't have to work very, very hard to get any of these things. Okay, so that's all I have to say about the Debye model, and I'll just give you some references. So there's a book on statistical mechanics. It's a slightly advanced book, but it's a nice book by R.K. Patria. Okay. This I have not referred to you guys before because it's slightly advanced level. Okay, and then you should look at condensed matter books. Okay, there's one book which I like. It's by these authors called Ashcroft and Mermin. So what they have is a whole bunch of topics, and you can just go pick. So, I'm interested in phonons. So you go and look at the chapter on phonons, and it'll be self-contained. Okay, so what are the things you need to know to read a book on condensed matter physics? You just need standard ENM, standard statistical mechanics, standard quantum mechanics, and of course classical mechanics also. Okay, so one thing we already saw in this thing also, I had to refer to things in classical mechanics and quantum mechanics. So in some sense, condensed matter physics books are true applications of physics, where I mean all your ideas come together. So what is nice about Ashcroft and Mermin is that this book, if you're interested in a particular topic, say magnets, you go there and they'll have some 2-3 chapters on it, but you just go and you can just read those chapters locally, and as long as you know your basic physics properly, I mean, it's like reading a novel, and of course you need to put pen to paper. Okay, and then there is this other classic book by Kittel which I don't like. Okay, that's my personal prejudice, but it's what it has is nice, very good thing, experimental thoughts and things like that. So it's more like an encyclopedia than a textbook. Okay, Ashcroft and Mermin is closer to a textbook. But now both of these books are not something you can say I'm going to read from chapter to chapter. You got to read them with an interest. I have to read this topic, so let me look up various things. Okay, so these are just some references, and so I think I'm done with my lecture. Floor is again open for questions.
Sir,
Yes, Srimanta.
so this is out of curiosity.
Hmm.
The plot, the device plot, how does it match the experimental results qualitatively or?
No, yeah. So what people do is to, yeah. So yeah, it does. Yeah. So there is you have one free parameter you have to fit, which is omega d. You adjust that, and but in fact, Patria actually has given a plot of. Remember this plot that I drew of the density of states. Okay, so the density of states, which the Debye thing and a real material, and you can see that it's, even though it's a crude approximation, it's not so bad. Okay, so if you look at all these books, there might be plots of this thing. Maybe I will scan. I mean, I was debating whether I should take a picture of the book and put it here or something. If maybe I'll do that. Okay, maybe in this thing when I upload these figures, maybe I'll upload a couple of things. Okay, so yeah, of course, that's where the uh, we would not be talking of device model if it didn't agree with the experiment. Okay, so